will go ahead and start into chapter 13, and then I'll just find like where is a good place. But it's a story that I don't like to break apart too much. Oh, straightforward, yes. Oh, it's right there. It's usually in the drawer. Why do you close the drawer? Chapter 13 has only one topic, NMR, nuclear magnetic resonance. So we're going to full of lots of new jargon for us. So NMR, the topic of NMR, very jargon rich. I have a different set of slides that we're doing in class than what I've uploaded onto Canvas. And so on Canvas, I have what I call a full tutorial. It has like all of my words written out. If you would like to go again through like all of my words, I have them all written out. And then also I have kept Shino's tutorial on NMR as well. And so it might be useful to go through both of them. If you're this first time through, it's not quite clicking. So then, because again, this is not a simple concept. So the study of NMR is quite complex. So sometimes it takes thinking about it a couple of times to figure out, oh, I get it. I see how it works. So we're going to go through it today. And then, of course, next week, I'll pick up, do like just a little bit of review, answer like what are those questions that you're not just being able to like work out in your mind, and then we'll move forward. Okay, so let's go ahead and head into NMR. So we're going to start to talk about the fundamental principles of NMR first. Okay, so the fundamental principle of NMR is that atoms with odd number of protons or odd atomic weight have nuclear spin. And this is a fundamental property. They just spin. It's just something they do. They spin. So that spinning force is not very strong. It's 10 times the negative 10 to the negative 18. And so are they whirling about with lots of spinning strength? No. But they still are spinning. It's not a strong spin, but they are spinning. So since we are in the course, organic chemistry, the atoms that we care most about that have this property are protons. And so how in NMR we tend to write it like this, A1H, and carbon 13s have the property, so we write it out as 13C. So this is how we write out the atoms that we are most interested in evaluating for. So proton and carbon NMR is going to be our focus. So we can do NMR of other atoms, even with our instrument upstairs, but we're not going to focus on them of this course. For some of you who decide to keep going and take Dr. Joanne's inorganic chemistry course, then you'll look at some of the other nuclei that have the property of spin. Okay, so this spinning creates a small magnetic field. And so then each atom has this small magnetic field around it. So a little bit of compare contrast. So we talked about how in the last section, all bonds have a vibrational frequency. And if you have a polar bond that vibrates, it creates a small electric field. So with NMR, all of our bonds that spin, so all of our atoms that spin have a very small magnetic field around them. And so that magnetic field we refer to as a magnetic moment. And there are different ways that we can picture this. So let's start on the far left. So this far left is kind of how we often picture or draw spinning atoms. So I have an atom and then it's just spinning. I won't make all of you stand up and spin around. So I'll just do it up front. So that's often how we picture it. But what we know is that's not actually how atoms spin. How they actually spin is a little bit more like this, which I can't do very well. But what you can imagine is all of you have played with the top. And so we would have that top and we'd start it spinning, and it spins directly up and down at first. But then as it loses energy, what does it begin to do? Like wobble, and that's known as precession. And so we know that atoms actually precess. That's what they do. So that's what that motion is. It's a precession, but we just simply refer to it as spinning. So we just call it they're spinning, when really technically it is known as a precession. The easiest way to picture these atoms with spin is as if they are small bar magnets with a north and a south, and then the magnetic moment pointing in a direction. That's the easiest way to think about them in our mind. So I chose to draw my magnet with the moment going towards north, because if you're ever using a compass, the needle points what direction? Like north. And so that's kind of also easy for our minds to visualize as we're thinking about this complex principle. So in almost all of my other slides, I have us thinking about the atoms as teeny tiny little magnets with a moment going towards north. So our atoms, just out here, they'll spin in all different directions. That's what I'm representing on the left. So they will spin in any directions when they're not under any field. So when we're under no field, so there's no other magnet like in the room, there is no orientation of our spinning. So the atoms are spinning in any direction. Okay, but when we take our molecules, our chemicals, put them inside a magnet, so when we put them inside a magnet, we say now these atoms are under an applied magnetic field, then the atoms orient themselves to the field. So I'm sure several of you have played with bar magnets before, and so if I have two magnets and I bring them towards one another, they often snap together. With what ends? What ends snap together? Yeah, south and north. So the opposite poles snap together. And so that is the kind of orientation that we see in an applied field. That the north side of the bar magnets will align with the south of our applied field and vice versa.
So in this, we see the
Yes.
coming together.
Right. So did all of the atoms align in my figure? No, this is known as population dynamics. So we will always have some atoms that break the rules. So my question for you is, do all of you come to a complete stop at stop sign? It's the law, right? When there's a police officer, that was my other answer this morning. So this weekend was my mom's birthday, so I was at home. My 15-year-old nephew had his learner permit, and so he was often following me in the car behind. I stopped at every stoplight. I can stop, and then I kept going. But do I always stop at stop signs? And I'm really bad, especially if I'm on the motorcycle. It's really annoying. You come to a complete stop, you have to go down, and then you start up again and bring your feet back up. And so at stop signs, especially if there's like no one around, I very rarely come to a complete stop. So this is population dynamic. We have our rules, and then there's going to be certain numbers in our population who will break the rules. Same things happen with our atoms. So then when we take our atoms, we put them into an applied field. Most of them are going to orient with the field, but not all of them. And so then that's why I have these two different populations. Okay, so with these two different populations, those that align with the magnet say that they are in the low energy alpha spin state. Those that are aligned against the magnet are in the high energy beta spin state. The difference in energy in between is a delta E value that we can calculate. So protons have a very specific delta E value. Carbon-13 atoms have a very specific delta E value. And the delta E value for each kind of atom is different because in this delta E equation, which we're not ever going to solve on paper, but in this delta E equation is the gyromagnetic ratio. So gyromagnetic ratio. And so ratio, that is kind of how I think of it, is strength of gyration, strength of movement. So the gyromagnetic ratio for protons is different than the gyromagnetic ratio for carbons. And so the delta E for each of those two different kinds of atoms is going to be different. This is another key principle of NMR. So we have these two different spin states. There's an exact energy difference between the two different spin states. We have an equation that defines the ratio, and it depends on the gyromagnetic ratio of each of the individual atoms. It also depends upon the strength of the magnet, but we're going to focus on the gyromagnetic ratio. So now these are all the fundamental principles. So now we're going to get into how does the instrument operate? How does it work? Can we use this instrument to determine the structure of our compound? And as I've introduced before, NMR is so powerful. By itself, we can determine the structure of a compound. Is it helpful to have IR? Is it helpful to have mass spec? Absolutely. But we can solve for a structure by NMR alone. Okay, getting into the operation. We have these two spin states. And so with a delta E value, this is a tiny delta E value of about 10 to the minus 5 kPa per mole when we're inside of a 25,000 Gauss magnet. So a pretty strong magnet, and still that delta E value is only about 10 to the minus 5 kPa per mole. So this energy difference between the two spin states exactly matches the energy within RF waves. So this would be radio frequency waves. And so how the instrument operates is that we irradiate with radio frequency waves. And when we're at the right frequency, then we flip the spin of our atoms from the low energy alpha spin state into the high energy beta spin state. So it will absorb the frequency and flip the spin. So the instrument operation is a lot like IR. We just go frequency by frequency, and then we determine which frequencies are absorbed and which are transmitted. And so when a frequency is absorbed, then we know we have flipped the spin of a certain kind of atom into the beta spin state. So it absorbed that energy, so it absorbed that photon of energy, flipped the spin into the high energy spin state. Okay, but will all atoms absorb the energy and flip the spin? So this is picture number 2. Will all atoms flip their spin? The population dynamics again, but most of them will flip the spin. Okay, and then when we flip the spin of an atom, it is said to be in resonance. So we flip the spin, and now the atom is in resonance, and that's where the name of this instrument now comes from, nuclear magnetic resonance. So nuclear, this has a lot to do with the number of protons that an atom has. Where are protons found? In the nucleus of an atom. So that's the word nuclear. So nuclear magnetic, we are taking our samples, we are putting them inside a magnet, and then we are irradiating with frequencies to put those atoms into resonance. And then we record what frequencies were required to put atoms into resonance. So then we just have this long list of delta E values and the atoms that match the delta E values, and that's how we interpret NMR. That's the fundamentals of how NMR operates. So odd number of protons, odd molecular mass, then we have the property of spin. Inside a magnet, those atoms can either spin with or against an applied field. We irradiate with radio frequency waves. some of those wavelengths will be absorbed, and we record that in an NMR plot. What happens when we absorb the energy is that we are flipping the spin into the beta spin state. So that's the fundamentals. So some of you may have been inside an NMR. You just didn't know it. So the other name for NMR, the human version of NMR, is known as MRI. So magnetic resonance imaging. And so then we lay our bodies on a table, and then what do we, I've actually never had an MRI. I just watched lots of movies with MRIs. Okay, and then the bodies go into, what are they split into? A really big magnet, which is why you can't be wearing anything metal or can't have anything metal. So actually, my back is mostly metal. I can't actually go into an MRI. So my back is totally fused, and so I could have some metal pieces. My rods were taken out, but I could have metal that's still back there because it would have gotten caught within the bone when my bone grew over the top of the metal. Not really a good idea for me to go to. Because it's just this really huge magnet. And so that's exactly what MRIs are, right? Right, tiny, because they've determined through experimentation, like what can actually go into an MRI and be safe. No, you're exactly right. Some pieces of metal.
They were like, oh, you didn't need to speak that out.
Yeah. And then for me, any metal I have remaining might actually be encased within the bone of my spinal cord. So also might not necessarily be a problem, but I'm not sure.
It's scary.
Yeah. So what's good is I've not ever had to have an MRI. But yeah, that's it. So our bodies lay on the table, we slide into that table, and that's MRI. So it used to be called an NMR, and then no one would get into it. Nuclear magnetic resonance. I'm not going into any instrument with the word nuclear in it, because I'm going to come out growing green, or it's going to fill me with radioactivity. And so they had to change the name of the instrument to magnetic resonance imaging. So they took out the N and just kept their MR, and then added I for the imaging. So magnetic resonance imaging is now what we do. Okay, so I want to go ahead and go through like the basics of the instrument. And I think that will be a best time for us to take a break. So let's go through the basics of the instrument. So this is like our general outline of an NMR. So we went through a general outline of an IR the last couple of weeks. And so let's go ahead and start at the sample. So we have this sample tube. So we are going to take our unknown sample and then we are going to put it into a tube. So a couple of things about this process. We do not have a solid state NMR. So our samples have to be within a liquid. That means that we have to dissolve our samples in a liquid. They also need to be at lower concentrations. You have to be a little bit careful with concentrations. So we need low concentrations. We need it in more of a liquid form. And so we have to dissolve. There is a problem right here at the very beginning. So here's our problem. Let's say our unknown is something like this. And I need to dissolve it. Okay, well this 1, 2, 3, 4, I have branching. Oh yeah, I could probably dissolve it into water. But what kind of NMR are we doing? So Mariah, you're already shaking your head. What do you see as the problem? Well, so actually you're highlighting one potential problem that could happen. And so I'm exactly going to go there in just a minute. Any other problem that you see? Yeah, so I have 2 protons here that are also going to show up by proton NMR. I have protons in my solvent. And so it's really difficult if we have an unknown with like all of these protons, and then we have a solvent with all of these protons, and their signals, their peaks are going to be right on top of each other. And so what we dissolve our samples into, we have to very carefully consider. And so instead of using normal solvents in the lab, we use deuterated solvents. So deuterium is heavy hydrogen. And so then it does not have the property of spin. Instead, instead of dissolving in the water, we will dissolve in D2O. So then our solvent is not NMR active. And then here comes the significant expense of NMR. So we've had our NMR for years, I think almost 12 years. It has never needed repair. We've done some cleaning. It has never needed repair. But running NMR is expensive, and that is because these deuterated solvents are quite expensive. Instead of using deuterated water, what we use is CDCl3. So we use deuterated chloroform. Instead of CHCl3, we use deuterated chloroform. How many hydrogens have had to be replaced to form this deuterated solvent? Just one. And so it is not very expensive because chemistry has only been required to replace one hydrogen. Deuterated water will quite expensive because chemistry has had to have been done to replace two hydrogens, going from water to deuterated water. So we use CDCl3. So then the downside of that is that it's not a good solvent for everything. Sometimes you are going to see little bits of solid still within your NMR tube, but we've kind of figured out concentrations that work for us. So if we have a compound that really just won't dissolve enough for our analysis, then the go-to is deuterated methanol. So we do have some deuterated methanol around it. Okay, everyone pretty clear with that? So now let me go on to what Mariah said. So what Mariah was highlighting is, not only do I have a prodict solvent I'm considering, I have a prodict unknown. And that is definitely a problem. And here's what can happen, which is I can take my unknown. So what can happen? Oh, there it is. Lost my pin for a minute. So what is chemistry that can easily happen with these prodict materials? I lose the proton. So then I would go to the oxide and H+. So what can the deuterated solvent do? So my solvent, I'm just going to put solvent here. The chemistry that it can do is it can break apart and release a D+. So a deuterium ion. And then what can happen is that the O- and the D+ combine together within the tube. And this is not chemistry that we can stop. And then we would get this OD final product. Does the deuterium give a signal by NMR? It is not NMR active. And so what this can mean is that the hydrogen of an alcohol can get replaced by a deuterium. That deuterium will not give a signal, and so that can mask the presence of OHs. So we have an issue with analyzing for hydroxyl functional groups and amine functional groups because of this chemistry that will happen within the NMR tube. This chemistry is known as deuterium exchange. And so it will mask the presence of alcohols and amines. But wait, we have IR that will go along with the NMR. And so then will we be able to get an idea about alcohols and amines by IR? Yes, they are quite apparent. Is there a little bit of ambiguity? There is between, is this a broad rounded peak or is this a spike? Yes. but we are going to see something by IR at 3,300. And so then that's how we're going to know, oh, and I do have these functional groups, but they underwent. That's kind of the key thing that I want to talk about first in regards to our sample. Okay, any questions before I move on to the next part? Okay, so our sample needs to be put down into a magnet. So the magnets need to be very protected because we walk around with like cell phones and other things that can influence magnets. And so our instrument is about like at waist height, that's about how tall it is. And the magnet is down kind of more in the center of the instrument. And so there's a method that we use to get this sample down in. So we do that by airflow. So when you have your sample, it's prepared, it's all mixed up. So we turn on the air, and there's airflow going up this very thin metal tube. And what we do is we place our sample into that metal tube with the airflow coming up, and now the airflow kind of goes around the side of the tube. And then to get our sample into the magnet, we turn off the air, and then our sample just slides down into the middle of the magnet. That's that part. So pretty straightforward, but then there's a little bit of airflow that kind of keeps going around the tube. It's directional. So how the air goes into the tube, it feeds in a certain direction so that our sample will also spin. On most of the lids, what you'll see is that we've drawn a little line so that when the sample goes in, you can look down, and we have a little flashlight so that you can make sure it is actually spinning. Sometimes we have to play with the airflow just a little bit to get it to spin. But with that line, then you can tell if it's just sitting there, you can see the line, but once it starts spinning, then the line goes invisible to our eyes. So we want it to be spinning. So all that goes usually pretty straightforward, great. But now we have to think about getting the sample out. Here's where we need to be careful, because we're ready to take out the sample. And so what if we take that ear knob and just go whoosh? What's going to happen to the sample? Yeah, it's going to pop up and can fly. So we think we have our airflow tuned to where you actually can't shoot the sample too far. But when we turn on the air, it should be you kind of just slowly turn it over. And then the sample comes up and then just kind of bobbles. So that's the part of like putting in the sample to our instrument and then bringing it back out of the instrument. And now let's go ahead and go into the rest of the instrument. So when it settles down inside the magnet, there is going to be a controller that controls the exact strength of the magnet. And then we also have an RF transmitter, so then that would be a radio frequency transmitter that controls the frequencies that we're shooting in at our sample. The easiest way to think about NMR in your mind is that we're holding that magnet at one strength, and then we just go one frequency at a time, making our way all through the appropriate radio frequency. So this is exactly how we thought about IR. I'm just going through one infrared frequency at a time. That's the easiest way to think about our instruments. In terms of instrument design, it has been found that it is less difficult to shoot one frequency of radio waves, but then go one magnetic strength at a time. Because both frequency and magnet strength are in that delta E equation, so we can change either of them. Our instrument actually changes magnetic strength. So we shoot with one frequency and then we work our way through all different strengths of magnet. So that's actually how ours works. But thinking about it the opposite way is not wrong. That is the original design of NMRs, was one frequency at a time with an RF transmitter. Okay, and so then we're transmitting our wavelengths through. We record from our detector which wavelengths were absorbed, which ones were transmitted, and then we get a set of peaks, and then we interpret those peaks. So these set of peaks match two very specific delta E values, and so then we know exactly what kind of atom is absorbing that frequency, and then we can fully determine the structure of NMR. Okay, so now that we've gone through the instrument, I think that this is a great place to take a break. So when we come back, we will talk about the real power of NMR. So I have our slide pulling up, and now we are to the power of NMR. So you guys are all of the basics, like some fundamental, like almost physics principle about the operation of NMR. We've gone through the instrumentation of the NMR, and now we're to the power of NMR. Now, it all comes down to this delta E value. So here's one of the key facts again. So our atoms of interest, and for organic chemistry, it's protons and carbon-13s. Each atom has a different gyromagnetic ratio. And so then that means the delta E value is very different for each of these kinds of atoms. And so what we are able to do is we are able to choose a certain bandwidth of wavelengths, irradiate with that certain bandwidth of wavelengths. And since the gyromagnetic ratio for protons and carbon-13s is different, then we will only flip the spin. We will only put into resonance one kind of atom. And so my example here on this slide is, let's say that I'm in a 14,000 Gauss magnet, so I have a 14,000 Gauss applied field. I have my chemical of interest, my unknown, within that field. If I irradiate with about 15 megahertz, that is going to flip the spin of the carbon-13 atoms. So that is the delta E value, that's approximately the delta E value for carbon-13 atoms. So coming back to my resonance demonstrator, and I know again, some of you in the back, this is a little bit harder to view, but with my resonance demonstrator, so what I'm trying to relate to you is we will only flip the spins of the atoms whose energy difference exactly matches the energy we're providing. And so in my molecule, I might have this collection of protons, carbon-13s, and fluorine atoms. But if I irradiate with just one set of frequencies, so if I irradiate at 15 megahertz, what are going to be the only atoms I put into resonance? So only the carbon-13, because only the atoms whose spin value, that delta E value, matches the energy that we are providing will flip their spin. It has to be an exact match. And so at 15 megahertz, that's about the match for carbon-13, and then 60 megahertz is about the match for protons. And so that's kind of the first thing that's powerful about NMR. Our NMR, we have different capacitors. So if some of you have done electronic work, we have different capacitors for the different kinds of atoms. And so we just put in different capacitors depending on which atom we're wanting to look at. So our instrument is usually left at proton NMR work. And then we'd have to do some changes to do carbon-13. We'd have to do even more of a change if we wanted to go out to fluorine or phosphorus. But if you're in inorganic chemistry, like I mentioned, you will probably do some of that work in inorganic chemistry as well. That is one thing about the power of NMR. But then here's the other. Not every proton is the same. Not every carbon-13 is the same as other carbon-13s or as other protons. So our protons, often we think about them as being naked. So this is my example of a naked proton. So a naked proton would have a very particular delta E value. But our atoms are protected by electron density. So if we have electron density surrounding an atom, then that creates an induced magnetic field in the opposite direction of the applied magnetic field. So it protects the atom from the magnetic strength. And what that does is that increases the delta E value. But then I will have some atoms that are very protected by an electronic field. And then the delta E value is significant. That means it takes a different amount of energy to flip the spin of a protected proton from a naked proton. So this protection we call shielding. So electron density is shielding. So if I have a proton or if I have a carbon-13 that is very shielded, it requires a lot of energy to flip the spin, to put that atom in resonance. If I have other atoms that are less shielded, it requires less energy. And so we go frequency by frequency to figure out what all different kinds of protons do I have, from shielded to deshielded. And then we can go through another range of frequencies to go, what kind of carbon-13s do I have? Are they shielded or deshielded? So here's a way to think about it. Yeah, Abby, go ahead.
So that mean that
Uh-huh.
go
So one proton with lots of electron density, it has one like protection level. So like it's very protected. But then a proton in a different part of the molecule will have a different level of protection. And so a different delta E value. Am I getting at your question there?
yes. Not every single
Right.
range.
Yep, exactly. And I think this will become even more clear on my next slide. As we start like literally looking at a chemical, what this means in an actual chemical. So a way that you can think about it is, it's pretty cold outside. So what if you were all sitting here in your swimming suits? And I said, okay, field trip. I want all of you to go outside and to stay as long as you can until it's just too much cold and you have to come rushing in. And so delta E, think of that as being time outside. And so if you have just a swimming suit on, I sent you outside, I am putting you like in residence, I'm putting you outside. How long will you be able to stay outside? What is going to be your energy level for staying outside? So some of you, it might be you walk out and then you walk right back in. It's 30 seconds is the amount that you can stay outside. For some of you, it might be about a minute. And then you're gonna come right back inside. Okay, and so then that's kind of like this over here. We are not very shielded. Our body is not very shielded if all we have on is a swimming suit. But now, what if we were all like wearing a hoodie, nice pair of sweats, and then I sent you outside? How long would you be able to stay outside now? Longer. So that's a greater delta E value. And so then it's a greater delta E value. You're going to be able to stay longer outside before you're affected by the cold and you need to come in. So then this last step, what if we are well shielded? So we are well protected. So we have those like really fluffy coats on that cover your arms, make you almost like walk like the Pillsbury Doughboy, and it goes like all the way down to your ankles and zips up. So what if we all had one of those kinds of coats on? How long would we be able to stay outside? A lot longer. We are well shielded from the cold. It's going to take a lot longer before we have to come back inside to seek the warmth of the outside. So that's how you can think about the energy levels. And so then we have swimming suit protons, very little energy to flip their spin. So we have sweatshirt, sweatpants protons, a little bit more energy to flip their spin. And then we have those in winter coats, and it's going to take a lot of energy to flip their spin. And so hydrogen, so protons are different from carbons because of the gyromagnetic ratio, and then every proton is different from each other because of the shielding. Every carbon-13 is different from other carbon-13 because of shielding. So now let's look at a chemical and see how this plays out. So here's my example chemical. Oh, I just have here, what if it's low frequency waves? We would flip the spin of one. And if we had higher frequency waves, then we would flip the spin of the other. Let's go ahead and look at my example. So here is my example chemical I want us to think about. So it's an alkene So I have a double bond and I have an alcohol. Where do I have electronegative character? Yeah, so it's the oxygen. Oxygen atoms we know are slightly electronegative. Okay, and so then I'm going to write dipole negative. So I have dipole negative character at the oxygen. And then also as a reminder, pi bonds, a little bit on the electronegative side. And so they are dipole negative as well. Where do I have the most protected, the most shielded protons? Near the electron withdrawing groups or distant from the electron withdrawing groups? So the most shielded, the most protected with lots of electron density surrounding them. Near an electron withdrawing group or distant from an electron withdrawing? Distant, exactly. Because electron withdrawing groups are pulling electrons towards them and away from other things. And so I have the most electron density around a proton when I am distant from any electron withdrawing group. So for my example, what I have here is these protons in red. These are very shielded protons. So they are very shielded. So they have a lot of electron density surrounding them. It takes a lot of energy to flip their spin. So these are shielded protons. That's how we would refer to them. They are shielded. That's one language we use. The other way that we talk about these three protons is that they are equivalent to one another. These three protons have the same kind of shielding. So Abby, this is maybe getting at your question a little bit more in detail, I think, where you were going. So these three protons are considered equivalent. So all three of them are bonded to the same carbon. And that carbon is 2 away from an alcohol, 3 away from a double bond. They're in the same environment. They are the same, so we call them equivalent. So we have 3 very shielded equivalent protons. Okay, let's continue working through our model. What comes next? So then next, I have these 2 protons. These 2 protons also bonded to the same carbon, are in the same environment. They are equivalent to one another. Are they more shielded, less shielded than my red protons? Less, because they are closer to an electron withdrawing group, so they are a little less shielded. Let's march a little bit further to the right. So this aqua proton, anyone have a better descriptor for that color? We'll just go with aqua. So I only have 1 proton of this type in the entire molecule. It's a CH proton. It's 1 away from the double bond, 1 away from the electronegative oxygen. So is it more shielded or less shielded than those orange equivalent protons? Less shielded. Okay, and then what about this hydroxyl proton? More or less than the orange and red? Less, yep. And then what about this CH right here, my brilliant blue CH? More or less than my orange and red? Definitely less. I'm right at a pi bond, which is electronegative. So then these light blue C to H's, I have 2 equivalent protons here, more shielded or less shielded than my orange and red. Yep, less shielded. Okay, so now this is the complex issue. This light blue protons more shielded or less shielded than this brilliant blue proton? They are more shielded. They actually are, because I have 2 hydrogens on that side. And so then with that extra hydrogen, I do get a little bit more electron density. The other way to think about it is that brilliant blue proton is 1 away from the electronegative oxygen. who it is a little bit less shielded. So the brilliant blue less shielded is on the far right. And that is how we evaluate. And it'd be the same thing for the carbons. So these carbons on the far left, so my red and orange carbon, quite shielded carbons. And then I have more de-shielded carbons over here. So if we were doing carbon 13 NMR, we could walk through our molecule and kind of think about the shielding of those carbon 13. We're trying to, in our mind, almost predict what we would expect in the NMR. So Abby, follow-up question now that we've gone through our exact molecule, or is it kind of settling in? Okay. Any other questions before I move on? Because now we're going to leave fundamentals and go into interpretation. Okay, let's go into interpretation. So how I think of a molecule, this is not anything like you could draw in your notes. How I think of a molecule is almost like this Spartan rendering of molecules. So in my mind, I will see red areas, lots of electron density, blue areas with very little electron density. So in my mind, when I'm looking at a molecule, I see like all of this bodiness going on. And that may be where you get to later with just a little bit more experience. So if you would like another version of the fundamentals of NMR, this YouTube video goes into more of the math and the physics than what I go to. So I'm having you think about this quite a bit visually. But if you really love math and physics, you might appreciate this view of the fundamentals of NMR. Definitely gets a lot more into the math and the physics side. They have like a, a bicycle wheel that they have spinning. And they think of it in terms of like bicycle wheels and spinning and the magnet effect. And so you might like this other version with YouTube. But now, to interpretation. What I have here is a simple spectrum. Lots of things to talk about here before we can fully understand everything that's up here. So we have a scale from 0 to 10 for proton NMR. Sometimes when I give you data, you might see 0 to 11. The far right-hand side is referred to upfield and high field. That's how we refer to this end. So this end, we say is up or high. I usually tend to use the word up. So this is up to me. The other side is referred to downfield or low field. And so then I tend to refer to this as down. So I use the up and down terminology rather than the high and low terminology. Let's talk about where that terminology comes from. On the far right-hand side, we will always, a little bit air quote here, we will always have a peak at 0. That peak at 0 is for TMS, that's trimethylsilane. Trimethylsilane has the most protected protons in any known chemical. And so we use it as a standard in our instrument. So in our samples, we always have 1 drop of trimethylsilane, 1 drop of TMF. And so like on the bottle, you'll see CdCl3 with TMS. So that is set by our instrument at 0. All of the other peaks are normalized to 0, and the math I've shown you down here below. And so the math is, however far in hertz we're below TMS, divided by the strength of our instrument, and then that gives us a number. So we refer to that number as the chemical shift number. And so then its units are either written out in part per million, because over here we're dividing by mega million, so parts per million, or we say it has a delta value. So the chemical shift is 5 parts per million, or the chemical shift is delta 5, meaning exactly the same thing. It just depends on the chemist that you're talking to. And so we have this range of chemical shifts, usually between 0 to 10 for all of the protons. What this means is the most shielded protons have the chemical shift up here at the top, upfield, like 0 to 3. The most d-shielded protons are downfield with chemical shifts like 7, 8, 9, 10. Okay, so then that's the first part of NMR. So now I've color-coded everything. We talked about in my example molecule, those red protons are the most shielded. And so then I placed those red protons at 1. So CH3, protected CH3 protons are almost always found at 1. And so just like with IR, we're going to think of bands of where we expect data to fall. So for like all of our NHs, OHs, CHs, like around 3,000. All of our double bonds for IR around 2,200. Our triple bonds are around 22. Double bonds are around 60. So we're going to think of approximations for NMR as well. I'm going to flip forward one slide. Is there a table of values you could memorize? Yes. Do I find it worthwhile? No. I think we're going to do this enough that you're going to get a feel for NMR. You don't need to have these exact numbers in your head. So instead, I'm going to give you some ranges to think about. So for our ranges to think about, between 1 to 2, we have CH3s, and then, where's my pin at? There it is. And then CH2s, and then CHs, protected. So from 1 to 2, it is CH3, and then CH2, and then CH in order. So the CHs are slightly more downfield than any CH3, and that's kind of in the range from 1 to 2. So how I think of the range from like 2 to about 4, like around in there, is like I am 1 away. So that proton is 1 away from an electron withdrawing group. How I think of 4 to about 7 is I am at an electron withdrawing group. So 7 to 8, those are phenyl groups. Those are protons bonded to a benzene ring. So those are phenyl. That's all that we see in 7 to 8. And then above 8, that is where we tend to see the chemical shift for carboxylic acids and aldehydes. So these are our big bands and how we think about them going all the way from 0 to 10. So our TMS, our standard, always at 0. And then from 1 to 2, CH3, CH2, CH in order. 2 to about 4, 1 away from an electron withdrawing group. 4 to about 7, we are at an electron withdrawing group. And then 7 to 8 phenyl, and 8 above carboxylic acid and aldehyde. And this is a rough approximation that will work for almost all interpreting that you're going to do, because what kind of spectroscopists are we?
Budding.
Okay, and so again, like with IR, I may have you both predict an NMR and solve an NMR. So this is what we're going to be getting to get into a little bit more on Monday, is predicting and solving. And I have worksheets for us on Monday. Okay? And so then this is a really good way that we can do all of that predicting. Okay? Then some keynotes that I have here. I think the only thing that I haven't really talked about is like the 4th bullet point that is on this slide. So OH and NH, that deuterium exchange. So if we see them at all, notice here at the chemical shift of what, like 3.2, where I put it. So this would be like my prediction, where I predicted at 3.2. I predicted that signal to be just a little bit smaller, knowing it's probably going to undergo some amount of deuterium exchange. But what if it did a lot of deuterium exchange? What will happen to that signal? Yeah, it won't exist. It'll go away. And actually, for my work as a PhD student, what I would do is I did have OH groups. So I would run an NMR and then I would add deuterated water and then shake it up and then I would see which peaks disappeared because certainly deuterated water protic, I am going to get deuterium exchange and I would see what peaks disappear and then that also helps me assign all of my peaks and I would know which peaks were definitely from my alcohols. So that's kind of a trick of the trade. Okay, so what we're going to go into next, but not today, we're going to save most of this work for next time. So this is like a cliffhanger for this weekend. So you kind of know what might be good to read to get ready for Monday. So my cliffhanger is NMRs are not this simple. And it actually is a very good thing because it is the power of the NMR. So here is what a true spectrum is going to look like. So a few things about the spectrum. This is what we'll get more into on Monday. This is where we'll start on Monday. Every signal is actually split into peaks. So we call this splitting. And each signal has a very particular splitting pattern. And so we are going to answer the question of why. Why does it split? And why is like this 3 and this 5 and this 4 and this 2? So why does it split? All of that for Monday. So our peaks will split. Second important thing is all of our peaks do have an area that we have to pay attention to. When we think about area, I need to switch colors. I found earlier my color didn't work all that well. Okay, I'm going to go to green. So what we do is we take a line from baseline, we connect all of the tops of these, and we think about that area right here. So we say that this signal has a very particular area, and then we could take this signal, do the very same thing, use a computer to calculate, and then this area has a this signal has a particular area, and that will also have meaning to us. So we're going to go back to the old days, because yes, I am absolutely old. So in the old days, when I did NMR, I had to print 2 copies. So copy number 1, I would draw for myself pretty carefully these lines, and then I would cut out the shape. And then I would mask the shape. So let's say, I'm trying to keep numbers like whole numbers for us to do easy math in our heads. So let's say that I cut out this shape right here, this first one at the chemical shift of 1, and I found that this had a mass of like 3.2 grams. And then I come out here to the chemical shift of about like 6.5, cut that out, I masked it and found that this had a mass like of 0.85. These would be known as raw values, raw area values. So when we do our instrumental work, we will also get raw values. Okay, these raw values not very helpful. And so then we do what is called integrating, and that really is creating a ratio. So what is kind of roughly the ratio of the area of those two? It is about 3 to 1, and that's integration. That's all that integration means. It's a fancy word, but all that does is we kind of create a ratio of values. And so we say that this is a 3 to 1 ratio. And here I have kind of a notation of 3 protons versus 1 proton. We're going to better understand that on Monday. But that's, we can get some raw area numbers, integrate them to a big whole number, and that also helps us solve for NMR as well. Okay, so for Monday, you can read through how Wade describes the fundamental operation of an NMR. The figure that I used in my slides is the same figure that is in your textbook. And then you could read a little bit about splitting and area. But if your mind is not quickly understanding, you can wait for me to explain it on Monday. But like reading through it once can sometimes be a little helpful. Because then when I re-explain on Monday, it's going, oh, this makes so much sense now. I hope my explanation makes sense. But that's where we'll pick up on Monday. We are all done. So remember this. So sometime I'm going to take 7 minutes away from you.
Oh.